So you've heard about galaxies. I'm going to talk about the intergalactic medium, which is the vast space between galaxies, and mostly it's just filled with a tenuous gas, hydrogen and helium mostly, and a little bit of the metals that get spewed out of galaxies. The title of my talk is Realistic Simulations of the Intergalactic Medium, the Search for Missing Physics, and it might be a surprise to some of you that there's missing physics. So this is the story of the missing physics and what we're doing about it with blue waters. How do we know about the intergalactic medium? Well, we find a very bright quasar, which is a very distant bright source, and we take its spectrum, and what you will see along the line of sight is a vast number of absorption lines. Here, let's see if I can figure out how to use their pointer, not my pointer, which I have in my pocket that I can't use. I think I'll use this pointer. So this stuff, which looks like noise, is actually physics. It is the absorption due to the intergalactic medium along the line of sight to the Earth by discrete clouds of hydrogen. Every once in a while, this line of sight goes close to a galaxy and you'll get a big absorption, but mostly it's these little absorption features that are called the Lyman alpha forest, and this is how we know most of what we know about the intergalactic medium. That was a low-resolution spectrogram. Here's a high-resolution spectrogram, and most of these absorption troughs you see are due to the 1 to 2 transition in hydrogen. They're at different wavelengths because the universe is expanding, and they're redshifted to different observer wavelengths, okay? So this is all hydrogen in absorbers along the line of sight. There was a great revolution about 20 years ago where several groups, including my own, figured out what was causing this. And the answer is the intergalactic medium looks like a cosmic webwork. This web structure is formed by gravitational clustering of dark matter, but the intergalactic hydrogen-helium just feels that gravitational potential and follows suit. So now if we are here on Earth observing a distant quasar, this line of sight will intersect numerous of these filaments, and each one of those will cause an absorption of some strength, and that is the explanation. Now, when this was first done, as I said, by 3 groups 20 years ago, the agreement between the observations and the simulation was amazingly good. And we all declared victory and went on to other subjects. And here is actually an ancient slide that I stopped showing more than 10 years ago because I was on to other subjects, first stars, first galaxies. But at the time, the discovery was made with a 128 cube simulation in a tiny patch of the universe, 5 megaparsecs big. The actual lines of sight that we probe with quasar observations are billions of light years long. So it's kind of amazing that such a small simulation could make a scientific revolution. But the agreement was so good with the data that we had at that time that we all said, this is it, we're done. Well, not all of us. Some of us kept going for a while. We can, of course, now do much larger simulations. This is a 4,000 cube simulation in a 600 megaparsec box that I did probably 5 years ago on Kraken. And so what happened in the subsequent 20 years is the simulations got better, the observations got better. And don't you know, a discrepancy turned up. And that's what I'm here to talk about. So along the way, we've investigated with my collaborator, David Teitler, whether it's observational systematics. No. Maybe the simulation isn't converged. No. Maybe the simulation box size is too small. No. I mean, we've done all of these tests, and this discrepancy has persisted. So the thing that we're investigating is whether there might be a piece of physics that is not in the simulation, or maybe the fact that we don't have individual galaxies in our simulation that could contribute some of the H1 absorption, maybe that's also contributing. And so this new PRAC project is focused on several hypotheses, and we're going to explore them one at a time. And the one that I'm going to be reporting on today is this part here. Maybe there's some piece of intergalactic medium physics that we don't have in our simulations. So how do you quantify this discrepancy? This gets into, the arcana of this subject, but there are several ways to display it, and this is called the Flux PDF, the Flux Probability Distribution Function. What is that? It's actually very simple. You take a spectrum and you just count the number of pixels versus the absorption, how much flux has been removed by the absorption feature, and you just plot it up. That's the Flux PDF. And so here you see in red observations with error bars, okay? So the observations have gotten quite precise. In fact, these are 10 years old already. And in the blue curves, you see two of the simulations with the standard model carried out on blue waters. On this side, this is the transmitted flux. This is high transmission. So these are the very weak absorbers. On this side, low transmitted flux. This is low transmission. These are the strong absorbers. And what you see is that the simulations, the standard simulations, give too many high transmission absorbers and not enough low transmission absorbers. You might say, oh, well, I mean, you're really close. Maybe you've got the intergalactic UV background slightly wrong. But you can fiddle with the parameters of the standard model, as we've done here, fiddling sort of within the range of fiddleable parameters. And you can't get the right shape. Now, others have done studies where they say, okay, well, let's just really fiddle. Let's just make completely different assumptions about the thermal and ionization state of the intergalactic medium. Can you recover that shape? And the answer is yes. But it requires essentially an isothermal intergalactic medium, which is not something that falls out of the standard simulation at all. You get a power law relationship between density and temperature, not an isothermal relationship. So what we are doing is using blue waters to do an A-B comparison between the standard model on the left and a quasar model on the right. So in the standard model, you use an ultraviolet background, which is a homogeneous but evolving radiation background, to ionize the intergalactic hydrogen helium. That's what people have done for years and years. In the quasar model, we put quasars as point sources in the box, and these are time dependent. They're different luminosities. They have finite lifetimes. There's a lot of action there. And what that will do is change the ionization state and the thermal state of the intergalactic medium in ways that you cannot do with the standard model. So why is blue waters needed? The quasar model requires 3D time-dependent multi-frequency radiative transfer. If you do radiative transfer, you know that that's very computationally intensive. There is also this scale separation, which requires very large uniform grids. You must resolve the Lyman alpha forest absorbers in a box large enough to contain hundreds of quasars, and when you make that ratio, it suggests 4,000 cubed grids, like the one I showed you earlier, but now you've got to have hundreds of time-dependent point sources and do multi-frequency radiative transfer to boot. The other thing is, this is a new model, and model development requires a lot of tinkering. You need some high throughput computing, but you need to be experimenting more or less at scale. Not at full scale, but you need to do some hefty simulations as you develop the model. So those three factors together tells you that progress really requires a combination of capacity and capability and that only blue waters can provide at the present time. Why multi-frequency radiative transfer? Well, the answer is straightforward. Quasars have a hard ultraviolet spectrum. It's a power law spectrum. And if you ask, well, how far do those UV photons go? They go different distances from the quasar. So this is a small test run where there happen to be 2 quasars present in the box at that time. And you see, as we scan to higher and higher photon energies, the higher energy photons just penetrate further because of their longer mean free path. And then this picture right here, this is the aggregate photoheating due to this radiation field. And this is what we care about. We are photoheating the intergalactic medium inhomogeneously, and that, we believe, may give us better agreement with observations. So this slide summarizes our progress. The quasar model has been implemented and tested at low resolution. Here, low resolution means 512 cubed and 1024 cubed grids. These involve hundreds of time-dependent quasar sources that are placed to reproduce the observed luminosity function of quasars. We also vary the spectral index. They have a fixed lifetime of 45 megayears. We use 5-group implicit FLD for the radiative transfer. And this is done with the ENSO code, which has this radiative transfer capability in it now. And we use this wonderful toolkit, YT, that many of you know about for the inline halo finding between the time steps. The high-resolution science run is underway, but these take a while to run and take a while to complete. I was going to show you a movie of this, but because of our technology progress, I cannot. So I'll just have to show you a still. So this is from the 512 cube simulation, and here you see redshift decreasing here, and what you're looking at is patches of doubly ionized helium growing around multiple quasars, eating up the singly ionized helium, which was the starting condition. And this is quite a large box, 200 megaparsecs, and there's hundreds of sources in there, but the Lyman alpha forest absorbers are not resolved. So this gives you the gross evolution of what's going on in the universe, but you need much higher resolution, the 4,000 cube dimension, in order to do this and at the same time resolve the Lyman alpha forest. This is just a couple of graphs showing the heating effect that we care about. This is temperature of the intergalactic medium at mean density versus redshift. Time is flowing to the left. And here you see the onset of the quasar population and a heating by about 10,000 Kelvin, and then the decline as the quasars decline. So that's what we care about. Here's a few stills from the 1,000 cube simulation done in a somewhat smaller box. So this amounts to a 4 times increased resolution relative to the previous simulation. Here you see a slice of the baryon densities showing the filaments. Here you see the gas temperature showing multiple quasar heating zones. This is the singly ionized helium fraction. So here we are depleting the singly ionized helium as we convert it to doubly ionized helium. And this is the photoheating field, which is, when you think about the standard model, this picture would be one color. It would be like that. But this is what the quasars do. So this inhomogeneous time-dependent heating may be the missing physics. The other thing I would comment is we do all of this with non-equilibrium ionization. And so with the quasars coming and going, there's non-equilibrium effects here as well that are hard to just, assess on the back of the envelope. You really have to do the simulation. So here's my last slide. Maybe I'll get us to lunch early. These are the questions that we were asked to address. The key challenges are to do a high-fidelity simulation of the IGM, including inhomogeneous quasar ionization and heating. Why it matters may explain this discrepancy between theory and observation. Why blue waters? It's both its capability and capacity. Accomplishments, we've done some low-res runs, which are already kind of publishable, but the high-res is in progress. The Blue Waters team was very helpful with topology-aware scheduling, and for that we are very grateful. The broader impact is that this drove the development of this multi-grid flux-limited diffusion capability, which is already available in the ENSO community code. No shared data yet, and the products is, again, the MGFLD capability in the ENSO code.